Okay, I want to tell you a little bit about static equilibrium problems. Static equilibrium problems are problems where there is no acceleration, either angular or linear acceleration. So an object that is in static equilibrium has no acceleration and no angular acceleration. A equals 0 and alpha equals 0. So basically when if you're designing a bridge, building a bridge, or any other structure like that, you don't want it to move at all one way or the other. You don't want it to have any linear acceleration or angular acceleration. You want it to stay put. So how do you do that? How do you get it to stay put? Well, you need to have two conditions met. You have to make sure that the net force on it is 0 and the net torque on it is 0. If the net force is 0 and the net torque is 0, then you'll have no linear acceleration and you'll have no angular acceleration. That's the whole point. Let me show you a few cases where you can have one be 0 and the other not be 0. Well, first of all, here's one that the net force, here's a case, let's call this 1 kilogram. Here's a stick that's 1 kilogram. And you put a force off center, so here's the center of mass of it. You put a force off center, and there is a net force of 5 newtons, and there is also a net torque. So this thing is going to accelerate that way. What will be the acceleration in the x direction? At that moment in time, the acceleration in the x direction is 5 newtons over 1 kilogram. That's 5 meters per second squared. So it's going to accelerate that way, but it's also going to spin as it goes. So it's going to spin and accelerate to the right. Okay. Here's an example of a net force being equal to 0, but the net torque not being equal to 0. So the net force on this is, let's see, 5 newtons plus negative 5 newtons is 0 newtons. So A will be 0, but alpha is not going to be 0. Because can you imagine pushing on something two ways? Here, boom. If I push 5 newtons and 5 newtons, this thing is going to spin. The center of mass will stay put, but it will have an alpha. It will start to rotate. Here's an example of a net force equals 0 and the net torque, the net force doesn't equal 0. The net force in this case is 10 newtons. If this is 1 kilogram and this is 10 newtons, the acceleration will be 10 newtons divided by 1 kilogram. That's 10 meters per second squared. But it's not going to rotate. You're not rotating this time. It's going to just look like this. It's going to go that way because the net torque is 0. Why is the net torque 0? About that axis, do you see how this one is trying to rotate it clockwise and this one's trying to rotate it counterclockwise? So if you just put one force on there, it does rotate. But if I put 2 forces on there, then it doesn't rotate. That's because there is no net torque, but there is a net force. So alpha is equal to 0. Here's a case where the net force is equal to 0 and the net torque is equal to 0. So let's talk net force first. We got a 5 and another 5 plus a negative 10. So the net torque is equal to 0. So A is 0. Excuse me, the net force is equal to 0. So A is 0. But not only that, but the net torque is equal to 0. Why? This puts no torque on it because it's going right through the center. And this is negated, that torque from this one is being negated by the torque from this one. So the net torque is 0, so there's no angular acceleration. Okay, let me tell you then how to solve an equilibrium problem. There's basically 3 steps. Step number 1 is you're going to draw a free body diagram of the thing that you want to keep in equilibrium with the forces at their places of contact. So when we did Newton's laws, we didn't worry about, we just put all the forces at the center of mass. But we can't do that anymore. We have to put the forces where they actually occur because they provide torques. Those forces can provide torques, and where they occur matters. The other thing is that we have to choose an axis. Even though this isn't going to have any rotation, there won't be any rotation, we'll choose an axis so that we can talk about torques. And finally, we'll apply these three equations. These are the three equations to have something not rotate or accelerate. There is one in the z direction too. The net force in the z direction has to be equal to 0 too, but I'll just use these because these are what your problems use. So the net force in the x direction has to be 0, the net force in the y direction has to be 0, and the net force or the net torque has to be 0. Okay, let me show you how this works then. Let's say we have a plank that has a mass 2 kilograms, and it's being supported by two supports, support A and support B, and there's a 1 kilogram object that is 3 meters from this edge. And what we'd like to know is what will be the force from each of these fulcrums if it's just remaining motionless. Okay, so what you do is you first draw all the forces. So I know there's a force this way due to the one fulcrum, due to the one support, so I'm going to call that FA. And then there's a force this way due to B, so F sub B is straight up. This plank has a weight down of 20 newtons because it's 2 kilograms. Notice I'm putting that at the center of mass. And then there's this box that is 1 kilogram that's pushing down with 10 newtons. So it's actually, I should have put it right here. That's 10 newtons downward. I'm not drawing a force diagram of the mass. I'm just drawing it of the plank. Okay, so there aren't any forces in the x direction, so I don't have to address that. But I do know that, let's see, FA in the y direction, FA plus FB have to be equal to 30 newtons. See how that works? The forces in the y direction have to add up to 0. Okay, well, I have two unknowns and only one equation, but that's okay because I still haven't done my torque. I'm going to make this my arbitrary axis right there. That's going to be my axis. And the reason I'm doing that is because then this won't put a torque on it at all. FA will not put a torque on this because it's going through the axis. The lever arm is 0. So let me just say that the torques now, the battle of the torques, if that's the axis, we got these two that are trying to rotate it this way, and this one that's trying to rotate it the other way. For these, trying to rotate this way, and they have to, the torques there have to equal the torque trying to rotate it the other way. So it's kind of like this. If these two forces are trying to rotate it this way, but this force is battling this torque, and it's trying to rotate it that way. So let's show the battle of the torques. 10 newtons times 3 meters, this is 3 meters, plus 20 newtons times, that's going to be 4 meters. It's in the middle of the board. That has to equal, out of space there, that has to equal the force from B times, how far is that from the axis? All 8 meters. So at this point I can solve for FB. Let's see, that's 30 plus 40, that's 100 and that's 80 and 100, so it's 110. So FB is 110 Newton meters divided by 8 meters. So I got that.